I put together a series of questions that you can answer to verify that you got through this PowerPoint presentation and understood all the concept that we wanted you to understand. So Chapter 7 is entitled Probabilities and Samples, the Distribution of Sample Means. And this is a concept, the distribution of sample means is a concept that we're going to need to understand well in order to understand the material in Chapter 8, which is the hypothesis testing chapter. So one very important concept here that we need to harken back to is the idea of sampling error. So we know intuitively that when we take a sample from a population, as we discussed in class before, we're generally not going to get the same statistics from the sample that you would get from the population. So for example, if I take the mean of a population and then I just take a small sample from it, so say the population is our classroom, we take the mean on the score on a test for the whole classroom and say it's 80%, and let's say I take a sample of 4 people from the class, the chances that those 4 people are going to have a mean of exactly 80 is very small. But it will probably be close to 80 if that was the mean of the class. And of course we know because of something that we'll talk about a little bit later, which is the law of large numbers and the central limit theorem. As we increase that sample size until it's larger and larger and larger, it's going to get closer to the actual mean of the class, but there's going to be errors within the samples. So let's review the idea of sampling error. So what you have is a population parameter represented by the middle of this target that I'm showing here. So what you want to do with your sample is try to get as close to that target as possible, which is, say, the mean of the population. And what's going to happen is you're going to take samples, which we're calling scores, and each one of those is called a datum. Together they're called data. This is just a review of previous concepts. So we take 3 scores and we get a mean from them, let's say. Okay? That mean is going to lie around right here where this yellow arrow is. And when I say mean of those 3 scores, we're just saying there's a location that is generally in the middle of all of those scores. That's how you can think of the mean right now. We could even think of that on the x and y axes. And what I'm showing here in green is the fact that that mean of those 3 samples from the entire population is not going to be the same as the actual population mean. Okay? And that is the concept of sampling error. So what we're going to explore in this chapter is, even though we can't get exactly the population mean by taking a sample mean, there's some interesting consistencies that we need to remember that will help us understand how we can have a foundation for statistics. There's some interesting consistencies about how samples behave and how sample means specifically behave when we take sample means from populations. So that was the concept of sampling error, and now we're going to talk about this idea of the distribution of sample means. So we talk about the distribution of sample means. We're talking about all of the possible means of sample size n. So for example, if we have a class of 30 students and say we have a sample size of 2, think of all the possible times you could take 2 people out of the class and take a mean from them. You could end up picking 2 individuals twice, right? So for example, if we had Lorraine and Olga. Okay, so Lorraine and Olga is the first sample, and that means if we take another sample, we could end up having Lorraine and Marco, something like that. Okay, so these are samples with replacements, like we talked about previously, but also they're always of sample size 2. And if we were to take all those samples of size 2 and take the means of all those samples, we end up with a distribution of sample means. Some of the means we get are more common, some of the means that we get are more rare. The ones that are rare are going to be at the edge of a bell curve, and the ones that are more common are going to be at the center of a bell curve. Okay? And there's some special reasons or foundational factors which we can say, if we fulfill these foundational factors, yes, then we can expect this bell curve. And we talked about that before, and I can talk about it a little bit more today. So There's different likelihoods, like I said, of each of the means of those samples of 2. And we want to know, are there consistent features to this distribution of sample means? And of course the answer is yes. We've already looked at this. We looked at this in lab. But I'm talking about it a little bit more here just to reinforce the concept. So what are the consistent features? Well, just like I said before, most of the means that you're going to get are going to lump near the mean of the population. So most of the sample means that you get are going to be near the population mean. Just not all of them, and you can't guarantee they're going to be exactly the population mean. And you're also going to get normally distributed distribution of sample means, okay? As long as certain criteria are fulfilled. We'll discuss that in a bit. But on a general scale, the larger sample you take, the more accurate you're going to have an approximation of the population mean. And again, that's sometimes referred to as the central limit theorem, the law of large numbers. So now, let's talk a little bit more about the distribution of sample means and the central limit theorem. So the central limit theorem is telling us that as long as the population is normal, okay, so you think about how the scores are distributed in the population. Generally, we're dealing with a lot of normally distributed populations, but sometimes there's population distributions where the values that we get from the population are skewed, let's say. So one really good example, which you probably noticed doing your first computer assignment, is that if you did any sort of plot of the length of words, you may have noticed that the data was skewed. So for example, shorter words, 2, 3, 4 letters long, are much more common than longer words, say 23 letters long or something. And you see this skewed distribution in word length just in general in the human language. In English, we can see from our lab report, but it's probably true in other languages. So you get a skewed distribution with a lump near 2, 3, or 4 letters long, and then a long tail, because there are some long words, but there's not that many of them in our vocabulary. If you were to take a series of means from that population of last names, as long as you took sample sizes of 30 or more, then the distribution of means that you get are going to be normally distributed. That's part of the central limit theorem. So let's review what I mean by that. So I would have to take 30 last names. Okay, conveniently that's the size of a class. So I take all the individuals in the class and I average what is their last name length. Okay, and let's say I go to another classroom and I take all the individuals in that class. Say all the classrooms are around 30. So we'll always use the sample size 30. As long as I always use the sample size of 30 or more, then if I take all of the means that I would get by lumping them into one distribution, I would see that the scores are going to pile up around the mean of the original last name distribution, and it's actually going to be a normal distribution even though the original distribution was skewed. So that, again, is something that we saw when we were doing those interactive demonstrations in lab last week. So we know something about the shape as long as we have more than 30 as our sample size. And another criteria is, if we originally had a normal distribution, well then we actually don't need a large sample size. As long as that original distribution is normal, then we're going to get a normally distributed distribution of sample means. Let's talk about central tendency. So central tendency is referred to sometimes as expected value. Okay, so the expected value of m, which is the mean of the samples, is mu, the population mean. This gets a little bit theoretical, but it's fairly easy to understand. Even though you're not always going to get the exact population mean as the mean of any sample that you use, you're expecting to get somewhere close to that. You're expecting to get that. And the best thing to expect would be the actual population mean, even though you don't always get it. Okay? So that's why we call this value an expected value. The expected value of m, the mean of any given sample, is mu. All right? So that's one factor we think about central tendency. And also, as I mentioned before, as we get closer to, or as we get larger and larger sample sizes, our mu number is going to approach, or sorry, our sample, the mean of our distribution of sample means is going to approach mu. This symbol here got a little bit messed up in the translation of my PowerPoint presentation. What this is supposed to say is m sub mu. Okay, that is the mean of the means. Okay, so m sub mu, meaning there's a subscript, m sub m, that means it's the mean of the distribution of sample means, m sub m. Okay, variability, now we're going to talk about what is the standard deviation of the distribution of sample means. That's sigma sub m. Okay, that's what that symbol should say. If you take these samples from a population and you make sure the sample size is at least 30, or at least that the population is a normally distributed population, then you're also going to have this interesting fact that the standard deviation of that distribution of sample means is going to correspond to the original standard deviation of the population divided by the square root of the sample size you used, which is also equal to the square root of the whole value of sigma squared over n. Okay, that's just a different way to say it. Again, that would be put sigma squared over n in parentheses and take the square root of that entire value. Okay, these two are equivalent equations. And what we call this is the standard error of the mean. Okay, this central tendency value is the mean of the distribution of sample means, and this standard deviation here is, we call it the standard error of the mean. So again, the law of large numbers says that m value, any sample mean value, is more accurate as we have larger sample sizes, which intuitively makes sense to us. And we want to know, how is standard error related to sample size? Well, we should be able to figure that out from the last slide. So if you want to take a moment, you can pause the lecture right now and try to figure that out for yourself. But think about, if this is the equation for standard error, and we were to have larger and larger sample sizes, we would increase the size of the denominator in this fraction, and therefore decrease the total value expressed by the fraction itself. Anytime we increase the denominator of a fraction and keep the top of the fraction the same, the actual number in the fraction gets smaller. Okay, so as the sample size increases, the standard error, also known as the standard deviation of the distribution of sample means, it gets smaller. Here's a series of questions that you can take a look at. These are from the book. Not going to go over them here. This is part of my lecture generally, but we'll move on from the point we're at into the rest of the lecture. If you want to take some time to answer these questions for yourself, you should hopefully have a way to understand how to answer them now, given what we just talked about, and you can check the answers that are in the book. Okay, now let's move on and talk about probability and the distribution of sample means. So here, for example, is a distribution of sample means. Again, the sample size is at least 30, or we have a population that is normally distributed. And you can see over here in the caption it says the distribution of sample means for sample size of 25. Samples were selected from a normal population with a mean of 500 and a standard deviation of 100. Now, when we talk about probability and the distribution of sample means, we need to think about the way that we view any distribution. When we see peaks in the distribution, we think about things that are more likely, right? And when we see long tails in the distribution, those correspond to areas where things are less likely. And what you see right here highlighted in orange is a point that is how many standard deviations away from the mean? It's 2 standard deviations away from the mean. And if you check your z-score table, you'll realize that if you cut off a distribution at about 2 standard deviations away from the mean, you're going to get to a point where you've got about 2.5% of the distribution on one side of that bar, on the tail side of that marking point that lies at 2 standard deviations away from the mean. So if we were to look at this distribution and say, for example, ask yourself the question, what's the chances of getting a mean? Now, we're talking about means here, not scores. Sometimes we were talking about scores in previous chapters. Now we're talking about what are the chances of getting a mean that is greater than 540. And again, if you look it up in your z-score table, we're at about 2 standard deviations away from the mean. And if you look up in the z-score table to the tail of that point where that z-score lies, you're going to see that you have about 2.5% of the distribution lying here. So you could say that you have a 2.5% chance of seeing a mean from the population that these means come from that is above 540. And you're going to see that we're going to use this kind of reasoning to help us understand how to interpret our experiments using statistics. How we're going to use this understanding of probability and the distribution of sample means to make conclusions about whether experiments are successful, meaning if they show that some change is significant or not. Here's another graph to give you a similar idea of probability and the distribution of sample means. Now we're looking at a point that is its own number of standard deviations away from the mean. So now instead of thinking about, okay, well let's say we're going to go 2 standard deviations away from the mean and we're going to see where about 2.5% of the distribution lies to the other side of. Now let's say, what if we wanted to ask ourselves what values are in the middle 80% of a distribution of sample means? Now, here we have a graph showing that middle 80% if we have a sample size of 25. Samples are selected from a normal population, as we said before, so we can assume there's a normal distribution of sample means. And now we have the population values for mean and standard deviation. That means if this is the distribution of sample means, what's the mean? The mean of the distribution of sample means is generally going to be the mean of the population. So the mean here would be 500, right? And what is the standard deviation of the distribution of sample means? Well, the standard deviation of the distribution of sample means, if we look at the previous slide, is this equation, sigma over the square root of n. Okay, so if we think about it, sigma is 100, and the square root of n, 25, is 5. So 100 over 5 is 20. And that's why we see a standard deviation of 20 for this distribution, which is the distribution of sample means. And now let's say we want to say, what is the likelihood of getting a sample, what sample means would we expect to get 80% of the time? And what we would do is we would look up in our z-score table, where does 80% of the distribution lie? We could say, what z-score corresponds to 40% from the mean to the z-score. Okay? In this case, you would have to look that up in the z-score table, and you would find that you would get to a z-score of 1.28 standard deviations from the mean. that way you would be able to say, okay, now I have 40% of the distribution over here. And of course, if I take the positive version of that z-score, I would have 40% of the distribution over here. And now since these are z-scores, if I want to translate that into actual scores that are in the distribution of sample means, what I'm going to have to do is multiply the standard deviation, 20, times the z-score. And that will give me the values between which I have 80% of the distribution of sample means. Again, this number 5.256 would be found by multiplying 20, the standard deviation, times 1.28. The z-score corresponding to the cutoff point between 40% of the distribution and the mean and the rest of the other 50% of that half of the distribution. And if you haven't got that, of course, you can take a moment to think about that, see if you can figure out how that all works out yourself. Again, here's some questions that you can work on to see if you understand things well. We do have our own sheet of questions, which I'll be asking you to fill out and collect that to ensure you understand things. But here's some things that correspond to what we just talked about. You'll find these questions in the textbook, and you can also find the answers and explanations there too. Now, more about standard error. And remember, what is standard error? Standard error is the word we use to name the standard deviation of the distribution of sample means. Before we talked about just standard deviation, and we're talking about the standard deviation of a population of scores, or even a sample of scores. Now we're talking about a very specific type of standard deviation. This is the standard deviation of the distribution of sample means. So this graph is just showing you that distribution and giving you an intuitive idea that, as we saw in the interactive displays that we did in lab last week, you can draw a few means at a time, you can draw a few scores at a time, whatever your sample size is, and then take a mean of that, and that corresponds to one of these, say, boxes. All right, and then you could take another mean of however many your sample size is, and then you're going to get another mean that would be represented by these boxes. And as you pile these boxes and boxes and boxes on top of each other, corresponding to whatever mean you get, you'll see a peak corresponding to the population mean, and then a bell curve which tapers off towards the extremes with a standard deviation equal to what? See if you can remember. The standard deviation is equal to sigma, the population standard deviation, over the square root of whatever sample size you're using. And again, we saw that in the interactive displays that we did in lab last week. Now, this is a very important thing to realize, that when you increase the sample size, as we saw earlier, the standard error of the mean decreases. Meaning, if you think relatively, what happens is your distributions end up getting narrower as you increase your sample size, okay? Which means that corresponds to a standard deviation that is smaller, or a standard error of the mean that is smaller. And we'll see later on, we all know intuitively that we want a larger sample size in order to make conclusions about things. But we're going to see in the next chapter how having a larger sample size corresponds to clarifying whether or not we can make a conclusion from an experiment. In a very clear way, we're going to see how that works. And one of the key factors here is that the larger sample size you have, the narrower the distribution of sample means gets. And just to give you a little preview, what happens is we're going to want to say, if we take a mean from a sample, do we think our mean came from a specific population? So if I have a population that would give me a distribution of sample means that looks like this, and I'm going to take a sample and I'm asking, is this from that population? Or maybe it isn't. If it isn't from that population, chances might be that the sample does not have a mean that falls regularly within this distribution. That mean could fall in the tail, and then we may be able to make a conclusion. So for example, if this is the distribution of sample means I would expect for cholesterol levels of people without medication, and let's say I give them the medication and then take the mean of that sample, I might expect to see a very extremely lower cholesterol. But you might be able to intuitively see at this point. You don't need to see it, but it's interesting to prelude this idea. You can see now that if I got a number, let's say I got a number of 60 for my cholesterol level, I want to lower it with the medicine. You can see how a cholesterol level of 60 given this distribution would look kind of like a big difference. Whereas if I looked at a cholesterol level of 60 compared to this distribution, it doesn't look like that big of a difference. So increasing sample size helps us really clarify whether there's a difference between a sample that we've taken and a hypothetical population that it may have come from. And this goes back to those questions of, okay, so what standard deviation would I pick if I have a score above the mean of the class and I want to look as good as possible? Right? We realize that we want to have low standard deviations to look better with respect to the rest of the class if we're already good. And we can go through all of the examples of those particular problems, but you can think about it in your head right now. Let's talk about one more. If I'm below the class average and I want to look better, well, now I want to have a larger standard deviation so that a score of 75, if the class average is 80, looks fairly normal, fairly close to the mean if this is a standard deviation. A score of 75 kind of looks worse in this scenario here on the right if we have a small standard deviation. Okay, moving on to the next slide. Now we want to talk about means, standard errors in our presentations in text. So if we're going to write a journal article or a paper about something that we've discovered, then we're going to have to mention mean, standard deviation, and now even standard error in our text. And so this is an example that we can use the text SE in italics capitals to represent standard error. And standard error, we'll see exactly when we want to mention that in the future. It's a very nice figure to report when we want to report in a bar graph and we want to look at the range of values that are generally expected around the mean that we have. So you can see in this bar graph we have two groups. One has a mean of 15, the other has a mean of 30, and here's the standard error of the mean, right? Well, you can see that the standard error is a nice clue to what's generally expected, and you see what's generally expected in each of these groups is not overlapping. And that may indicate to us that these are distinct groups for whatever reason. Maybe group A has a cholesterol treatment where it lowers their cholesterol and group B does not. If these standard errors overlap more, we're going to be less credulous about the fact that these are different groups. Okay? So that's one reason why we might want to show standard error graphically like this. Okay, Again, more questions. If you look these questions over, see if you can answer them. But again, you can also look at questions on the sheet that we've given you and really try to answer those to see whether you understand what we've talked about so far. Now, looking ahead to inferential statistics. So, we've talked about this a little bit already, but what we want to look for when we're talking about inferential statistics is we're going to have, say, a population of normal people with high cholesterol, let's say, people with high cholesterol, and we're going to give them a medication, and we want to see, does that lower their cholesterol level? So, irregardless of what healthy cholesterol levels are, we can think about if somebody has a cholesterol level of 400, and we want to say, we did our experiment, we gave patients the drug that was supposed to lower cholesterol, and we want to see, did it actually lower their cholesterol? What inferential statistics does is it says, listen, let's cut off the ends of the distribution of sample means. Let's cut it off here on the left and here at the right at the point where 2.5% of the distribution lies to the left in this tail and to the right in this tail. And let's say if we were to get a mean in that range, 2.5% of the time we might see it in the left, 2.5% we might see it to the right. And let's add this together and say 5% of the time, maybe, if we take a mean from just those people who had high cholesterol, we might get a mean in one of these tails. But if we gave them cholesterol drug, and then clearly we get a mean down here to the left of this line, wouldn't that give us a little more support for the conclusion saying our cholesterol drug worked? Because we can make a statement that says, listen, this is a mean that we might get from the distribution of people with high cholesterol. So it just could be a good day for these people. Somehow their cholesterol is, has been lowered because they didn't eat that steak last night. Or maybe you just happen to pick a sample of people that had the lower cholesterols in that group just by chance. If you did pick your people just by chance, there's really only a 5% chance that they would lie in one of these tails of the distribution. And so what I can do then is say, listen, even though they could have come from the distribution of people with high cholesterol, I'm going to reject that hypothesis. And I'm going to say, this is evidence or support of the idea that my drug actually does lower cholesterol. Again, you don't need to understand this completely right now. We're going to be talking about it more when we go over the chapter about inferential statistics. Some more questions to think about. Again, these are in the book. You can look for the answers there, and you can work on the sheet that I provided. And that's the end of this presentation. So if you have more questions and you need to talk to me in person, that's totally fine. We can discuss these ideas, and we'll have more time to discuss exactly how these play into inferential statistics when we have our lecture on inferential statistics.